Malware analysis is drowning in telemetry. When a suspicious binary detonates in a sandbox, the resulting report is a massive JSON dossier containing process trees, network flows, registry modifications, and extracted strings. A SOC analyst has to triage that data under extreme time pressure, cross-reference MITRE ATT and CK techniques, and assess threat severity. Large language models promise to automate that reasoning, but frontier closed-weight models are expensive, opaque, and raise serious data sovereignty concerns. Meanwhile, open-weight small language models can run locally on a single GPU, but they consistently struggle with complex behavioral reasoning. So here's the question that drives recent research at the University of Kent. Under a fixed single GPU budget, can orchestrated ensembles of small language models actually match or exceed a single frontier LLM when answering structured questions about malware detonation reports? The short answer is yes, but only if you engineer the workflow correctly. Raw parameter count doesn't solve the three characteristic failure modes of single-pass LLMs on this task. First, context overload. Full hybrid analysis reports routinely exceed model context windows, forcing truncation of critical network or payload telemetry. Second, surface-level pattern matching. Models latch onto conspicuous keywords like blockchain terms or Chrome overlays and classify based on that, rather than tracing causal execution chains. Third, domain knowledge gaps. Correctly interpreting specific MITRE ATT and CK techniques requires specialized malware knowledge that general pre-training doesn't consistently provide. The researchers tackled each of these by testing 11 general-purpose SLMs, 3 cybersecurity pre-trained models, and 6 frontier LLMs on the CyberSec Eval malware analysis benchmark. That's 609 multi-label questions stratified across easy, medium, and hard difficulty tiers. Because 74% of the questions are easy, overall accuracy is heavily weighted towards straightforward evidence retrieval. But the real test is how the models handle the rare, complex hard-tier questions that require multi-step reasoning. To amplify the small models, the team designed 4 distinct orchestration architectures. Let's break down exactly how each one works and why the fourth one wins. The first is an agentic pipeline. Instead of dumping the entire report into a prompt, the system chunks the JSON semantically at 51.2 tokens with a 64-token overlap to prevent boundary truncation. An enrichment agent scans those chunks for MITRE ATT and CK technique identifiers, and a curated vocabulary of 150 technique-indicative keywords. When it finds a match, it deterministically fetches the corresponding technique description from the MITRE SDIX API. Then a tool search agent generates and executes sandboxed, read-only grep and JQ commands against the on-disk report file to extract specific IOCs. Finally, an evidence miner calculates cosine similarity between the question embedding and every extracted snippet using a lightweight mini-LM sentence model. Anything below a confidence threshold of 0.65 is filtered out. This pipeline alone boosted QN3-4B from 16.58% overall accuracy to 25.11%. It solves context overload, but it still falls short on hard reasoning. The second architecture is a pure debate system. 2 agents critique each other's reasoning for multiple rounds. One is a general-purpose SLM, the other a cybersecurity specialized model. Each round, both agents receive the original prompt plus the full debate history, challenge the opponent's claims, and revise their rationale. On hard questions, this consistently improves accuracy, plateauing around 7 to 10 rounds. But on easy questions, accuracy degrades as rounds increase. The logs reveal why. Agents start introducing tangential information that pulls initially correct answers toward incorrect alternatives. In the literature, this is called drift. Pure debate is great for complex reasoning, but it's unstable for retrieval. The third is a hierarchical consult system. A tested general-purpose SLM can pose at most one sub-question per round to a cyber expert model. We can formalize this as a hierarchical loop, where an extraction function isolates the explicit query from the tested agent's rationale. The expert model acts as a stateless oracle that never sees the full prompt, and the tested agent updates its state using accumulated expert guidance. This consistently outperformed consulting a general LLM, but scaling the expert from 8 billion to 70 billion parameters yielded minimal additional gain. Consultation provides domain expertise, but it lacks the adversarial pressure needed to catch subtle reasoning flaws. The fourth architecture, the hybrid system, combines the best of both worlds and introduces a critical constraint. Phase 1 runs the full agentic evidence pipeline to produce a fixed evidence bundle. Phase 2 runs the debate, but every claim made by an agent must map to a supporting snippet in that evidence bundle with a cosine similarity above 0.55. This grounding constraint prevents the drift phenomenon observed in pure debate. If an agent can't cite the evidence, the response is flagged. Phase 3 uses a verifier agent to validate the final answer against the bundle, checking that the reasoning chain is internally consistent and that the selected answer has supporting evidence above the threshold. If verification fails, the system falls back to the answer most directly supported by the evidence, bypassing the debate conclusion entirely. The results are significant. The hybrid system, pairing QN3-4B with a cyber-specialized foundation SEC 8B, achieved 35.3% overall accuracy. That exceeds the strongest ungrounded frontier baseline, Gemini 3 Pro Preview, which sat at 34.77%. Performance gains held across all difficulty tiers, 38.14% on easy, 27.21% on medium, and 27.27% on hard. Ablation studies confirm both components are necessary. Removing evidence collection reverts to pure debate, dropping easy tier accuracy by 12.64 percentage points. Removing debate reverts to pure agentic, dropping hard tier accuracy by 7.27 percentage points. Removing the grounding constraint also degrades performance, proving that the similarity threshold actively prevents uncited claims from corrupting answers. But does this orchestration only help small models? The researchers ran frontier LLMs through the exact same hybrid pipeline. Grounding Gemini 3 Pro Preview boosted it to 38.22%. Grounding Claude Opus 4.5 boosted it to 36.85%. This shows the architecture is model size agnostic. The orchestration provides a general-purpose evidence-grounded reasoning framework that benefits all parameter scales. The open-weight SLM hybrid simply offers a locally deployable path that narrows the gap without incurring API costs. Let's talk about the operational trade-offs. The hybrid system runs on a single NVIDIA RTX 4090 at 4-bit quantization, using approximately 6 GB of VRAM. It costs $0 in API fees. The latency is about 105 seconds per question, compared to 3 seconds for Gemini and 4.8 seconds for Claude. For a high-volume, low-value alert triage pipeline, that latency might be prohibitive. But for a SOC analyst investigating high-value targets, reviewing a detailed detonation report, or operating under strict data sovereignty requirements, that latency is a reasonable exchange for transparency, reproducibility, and cost control. The two-phase design also provides natural checkpoints for human review. Analysts can inspect the evidence bundle before debate and intervene if critical artifacts are missing. Benchmarks tell one story, but real malware tells another. The team evaluated the hybrid on 12 wild samples exhibiting novel evasion techniques not present in the benchmark. The hybrid correctly classified 9 of 12, compared to 5 of 12 for the single-model baseline. Take UNC 5142, which uses a technique called ether hiding to store malicious payloads inside the data field of Binance Smart Chain smart contracts, instead of traditional C2 servers. A single LLM saw blockchain keywords, hallucinated cryptojacking, and missed the delivery mechanism entirely. The hybrid's agentic phase executed grep patterns for hexadecimal strings within the transaction logs, isolating the payload data chunk. The debate phase then correctly identified the contract as immutable data storage consistent with ether hiding infrastructure, classifying it as a dropper. Another sample, Llama Stealer using ClickFix, hid malicious PowerShell commands inside HTML clipboard event handlers. The single model saw the fake Chrome update overlay and called it credential phishing. The hybrid isolated the oncopy and onclick handlers, linked the base 64 encoded payload to known Llama C2 chains, and correctly flagged the clipboard injection vector. The hybrid corrected reasoning errors that defeated even the strongest frontier models. There are important limitations to acknowledge. 35% exact match accuracy is not sufficient for autonomous decision-making. This is an analyst assistance tool, not an autonomous triage system. The multi-label benchmark format differs from open-ended triage, and the system hasn't been tested against sandbox evasion, adversarial prompt injection, or keyword stuffing. Because retrieval relies on keyword triggers and embedding similarity, an attacker could theoretically promote misleading snippets or suppress relevant evidence. The parameter ratio heuristic for partner selection also covaries with baseline accuracy and architecture, so the 4-to-1 capacity balance should be treated as a benchmark-specific heuristic rather than a validated threshold. But for structured report comprehension, the findings are clear. Orchestration beats raw parameter count. This research shifts the conversation from chasing larger models to engineering better workflows. You don't always need a closed-weight billion-parameter model to outperform one. You need structured retrieval, grounded adversarial critique, and a verification loop. For security teams operating under budget and privacy constraints, orchestrating open-weight small models isn't just a cost-saving measure. It's a viable path to transparent, auditable, and highly capable malware analysis. The authors have open-sourced the full orchestration implementations, the evaluation harness, and the experiment scripts. I've linked the repository in the description. If you're building LLM pipelines for security operations, this is exactly the kind of architectural thinking that moves the field forward. Let me know in the comments which orchestration pattern you'd test next, and subscribe for more deep dives into the latest AI security research.